Regional analysis encompasses the study of hydrologic phenomena with the aim of developing mathematical relations to be used in a regional context. Generally, mathematical relations are developed so that information from gauged or long record catchments can be readily transferred to neighboring ungauged or short record catchments of similar hydrologic characteristics. Other applications of regional analysis include regression techniques used to develop empirical equations applicable within a broad geographical region. Regional analysis makes use of statistics and probability, including joint probability distributions. Joint probability distributions are useful in regression theory. Probability distributions with two random variables, x and y, are called bivariate or joint distributions. A joint distribution expresses in mathematical terms the probability of occurrence of an outcome consisting of a pair of values. In statistical notation, is the probability p that the random variables x and y will take on the outcomes x sub I and y sub I simultaneously. A shorter notation is the sum of the probabilities of all possible outcomes is equal to unity. A classical example of joint probability is that of the outcome of the cast of two dice, say A and B. Intuitively, the probability of getting a 1 for A and a 1 for B is 1/36. In total, there are 36 possible outcomes, and each has the same probability, 1/36. The distribution is referred to as the bivariate uniform distribution because each outcome has an equal and uniform probability of occurrence. Joint cumulative probabilities are defined in a similar way as for univariate probabilities, in which f of x sub k and y sub l is the joint cumulative probability. For the example of the two dice, the probability of A being 5 or less and B being 3 or less is the sum of all individual probabilities for all combinations of I and j, as I varies from 1 to 5 and j varies from 1 to 3. Marginal probability distributions are obtained by summing up p of x sub I and y sub j over all values of one of the variables, for instance, x. The resulting marginal distribution is the probability distribution of the other variable, in this case y, without regard to x. Marginal distributions are univariate distributions obtained from bivariate distributions. In statistical notation, the marginal probability distribution of x is. Likewise, the marginal distribution of y is. Returning to the two dice, the probability of A being equal to 1, regardless of the value of B, is. Likewise, the probability of B being equal to 4, regardless of the value of A, is also 1/6. Notice that the joint probabilities of each of all 6 possible outcomes have been summed in order to calculate the marginal probability. Marginal cumulative probability distributions are obtained by combining the concepts of marginal and cumulative distributions. In statistical notation, the marginal cumulative probability distribution of x is. Likewise, the marginal cumulative probability distribution of y is. Returning to the two dice, the probability of A being 2 or less, regardless of the value of B, is. Likewise, the probability of B being 5 or less, regardless of the value of A, is 5/6. The concept of conditional probability is useful in regression analysis. The conditional probability is the ratio of joint and marginal probabilities. In statistical notation, in which p of x given y is the conditional probability of x given y. The conditional probability of y given x is. From these equations, it follows that joint probability is the product of conditional and marginal probabilities. Joint probabilities can be expressed as continuous functions. In this case, they are referred to as joint density functions with the notation f of x comma y. Moments provide descriptions of the properties of joint distributions. For continuous functions, the joint moment of order r and s about the origin is defined as follows. With r equal to 1 and s equal to 0, this equation reduces to the mean of x. The expression within brackets is the marginal probability density function of x, that is, f of x. Therefore, the expression for the mean of x is. Likewise, the mean of y is. The second moments are usually written about the mean. For r equal 2 and s equal 0, this equation reduces to the variance of x. Likewise, for r equals 0 and s equal 2, this equation reduces to the variance of y. A third type of moment arises for r equal 1 and s equal 1. This moment is called the covariance. The correlation coefficient is a dimensionless value relating the covariance and the standard deviations, in which rho of x comma y is the correlation coefficient based on population data. The sample correlation coefficient is. The correlation coefficient is a measure of the linear dependence between x and y. It varies in the range -1 to +1. A value of rho or r close to or equal to 1 indicates a strong linear relationship between the variables, which large values of x associated with large values of y, and small values of x with small values of y. A value of rho or r close to or equal to -1 indicates a correlation such that large values of x are associated with small values of y, and vice versa. A value of rho or r equal to 0, that is, a zero covariance, indicates the lack of linear dependence between x and y.